welcome back, everybody. We have a video today in the spanning tree protocol, which is one of the harder topics to understand throughout the CCNA and very lengthy, but we'll try to make it as concise and short as possible here with Mohammed. How's it going today, Mohammed?
Good, good.
Good.
Let's get started.
Awesome. Cool. So did you want to explain to us why do we need spanning tree?
Of course. So mainly spanning tree, why do we need spanning tree protocol? The problem with redundancy, as you add more links in your network and your network gets complex, the redundancy links will give you reliability, but it will also create loops because of broadcast storms and unknown unicast packets slash frames. Um, So layer 2 has no TTL, so frames will circulate forever, and loops will cause broadcast storms, as well as MAC table instability. So where the same MAC address is seen on multiple ports as it goes through in a circle, through the network again and again in a loop. And it also creates multiple frame copies. So there is more congestion, there is CPU spikes because the MAC, the processing is so fast that when the loop happens, the CPU just goes uh, crazy with the whole usage. One loop can bring down an entire network in settings in seconds. And then if you go into details, the switch, flood, broadcast, and unicast, and unknown unicast frames, making loops multiply quickly. So in one network, if we have like two computers connected and they broadcast something and there is a loop, it's gonna the switch will broadcast everywhere, and if there's a loop, it's gonna go in a circle again and again and again and again and again and again. And the things that we discussed before, the max table instability, it's gonna happen because the same MAC address is gonna be coming from different ports because the destination, because of the destination and how the switch learns MAC address, like we learned in the previous video. And in real world, leaving STP off can cause floor-wide outages when someone accidentally patches a redundant cable. So if you take one cable and connect it again to another one of the ports, it's going to create a loop. And that's a real-world example of how STP, if you have STP disabled, a loop can occur.
Yeah. No, so thank you, Mohammed, for that. And for some of the newer folks that may be watching this, that may be wondering what TTL we're referring to, as we'll learn in our future videos, layer 3 or IP addresses do have a TTL, which stands for time to live, depending on the operating system. And the layer 2 world, that won't stop. So, in essence, think of a broadcast packet with three switches connected in a circle that goes on forever. So broadcast here, broadcast there, broadcast here, broadcast there. And one of the symptoms you'll notice throughout the network, like Mohammed mentioned, is those CPU spikes that will stop the switches from having any compute power to forward any more frames. So let's get into the fundamentals. Some of the spanning tree fundamentals. What spanning tree does, it allows you to create a loop-free logical tree on top of a physical mesh. So some of the fundamentals of that are it'll elect a root bridge. Each switch selects one root port, which means the best path to the root bridge that we just elected. Each segment has one designated port, which is a forwarding port, that and the remaining ports are placed in blocking state, but can activate if needed. So what that does, it creates a redundancy to your network, that blocking state, in case the two um, root ports failed, or the root port fails in your network, whether it's a physical failure or so on, it'll allow that blocking port to serve as the redundant path to get to the root bridge. So switches exchange BPDUs every 2 seconds to maintain topology. Let's get into what is a BPDU. As mentioned here, is a bridge protocol data unit, which is encompassed of a priority, as we'll learn, a VLAN ID, and a MAC address. So some of the standards and variants of the spanning tree are 8021D, which is the traditional, very slow spanning tree, which is what you'll learn in this video. Rapid spanning tree, which is 8021W, faster, modern, and it's what eight companies are doing nowadays. MSTP, which is multiple standing tree for load balancing, 8021S. And, there are multiple network vendors that you'll learn throughout your career, but I primarily see our STP being the favorite throughout enterprises. MSTP can be extremely good, very commonly used with Juniper networks. And then you get into Cisco PVSD Plus and Rapid PVSD, which is per VLAN versions, and again, very common if you are a Cisco heavy environment. Mohammed, could you get into the port states and roles of spanning tree?
Yeah. So, like Carlos mentioned before, there are different states of ports in STP. So here we'll talk about the 802.1d, which is the traditional version of STP. So STP port states in 802.1d, you have your disabled state, which is the admin down. Then you have your and that's like just you disabling the port, like going in the port and saying shut down. So it's going to show as disabled in your STP topology. Next is blocking. So this port, it will listen for the BPDUs, but it doesn't forward any data. So it will listen for all the topology changes going on in the STP, but it will not forward any data. Next, you have your listening state. This it will participate in the STP calculation. So it will help in like calculating the root bridge or the designated port, but it will not do any forwarding or learning. Next, we go to learning. Here you build the MAC address table, but there is still no forwarding. And as you go into the forwarding state, that's when you will forward traffic and you will learn MAC addresses and you will be part of the network essentially. And the whole process, what we call convergence, from where you go from like a blocking port to listening and then learning to forwarding, that will take 50 seconds with traditional STP. And that 20 seconds, I believe, is the blocking. Then 15 is listening, then 15 for learning, and then you go into forwarding state. And for the STP port roles, as Carlos mentioned before, there was root port. So root port is the best path to the root switch or the root that you elect. That, like Carlos mentioned before in the fundamentals, you elect a root bridge slash switch. And in this uh, picture that we have in the side, or like a lab we have in the side, here in this one, you can tell the root switch is switch one, because if you see on the links that are connected to switch one, they're known as those ports are known as root port or RP, and that tells you that that switch one is root switch. And a quick way for here to tell you is, if you look at the MAC addresses, the lowest MAC address is switch one. So we can make like a quick thinking that if they're all in VLAN one, the switch one will be the root bridge. Next, if we the designated ports, these ports, they forward the traffic for a segment. So the root port is the port that is toward the root switch, and any port facing other way from the root bridge or the root switch is going to be named designated port. Simple as that. Just anything away from the root switch is going to be designated port. And then there are non-designated ports, which is blocking. That is the link slash port that you will be blocking after the STP calculation. That will be blocked because you want to prevent the loop. So in this triangle of topology, if we don't block anything, by default, a laptop connects, like a PC connects, whatever, a broadcast is initiated, it's gonna go forever. It's just gonna keep going in the loop. We had to block one of the links to stop that. And due to STP calculation in this particular topology, it found out that the switch 2 port, on the switch 2, you will block the second port, and the one that is named blocking in the picture. So, and again, disable, you just manually shut down. So that's like you calculating yourself the whole topology and just be like, okay, I'm gonna shut down this link instead of like STP doing the job. So these are the different states and roles.
Right. Thank you, Mohammed. So let's get into how the root bridge is elected and the path and cost associated with that. So the root bridge election and using the same topology, one thing I want to note for all the viewers is there is a typo in this diagram, which, as you'll notice, the 32769 that is referenced in switch 2 and switch 0 is meant to be the same priority here. So this is meant to be 32769 as well. Um, so just looking at this topology, we know that switch 1 is a root bridge because it has both designated ports to switch 0 and switch 2, and the cost is the same, which we'll get into we got into that table, or I'm not sure if we have yet, that defines oh, sorry, it's here.
Yeah, it is.
So the 100 Mbps, which is a cost of 19. So you'll notice that if I were to go from switch 2 to switch 0 to get to my root bridge, that is a cost of 38. So it is much more efficient to go directly to switch 1 for the cost of 19. And the same logic applies for switch 0. If it were to traverse across switch 2 to get to the root bridge of switch 1, that 38 cost would be much less efficient than the direct connection. However, if we can imagine the link failing between switch 0 and switch 1, the link to switch 2 becomes our redundant path that it gets leveraged. Um, so let's get into the slide here. It is decided by the bridge ID, which is exchanged during the BPD use. The priority plus VLAN ID plus MAC address are the contents of the bridge ID. The priority default, so the default is 32768, but then we add the VLAN ID. So for in this case, we're talking about VLAN ID 1. So the priority default would be 32769. If we were talking about VLAN 10, the priority would be 32778. And this must be done in multiples of 4096. And the lowest bridge ID wins the root bridge process. So best practice in the real world is you manually set your core switch as a root priority of 4096. Sorry, as root with saying priority primary or make it root the primary or secondary, or you define the priority of 4096 and 8192. So the path cost, which is a short method, uh, the cost is based on link speed. So you get your 10 megs, which is 100 cost, 100 megs, which is 19, 1 gig per second, which is 4, and a 10 gig link is a cost of 2. The cumulative is that each hop adds a cost at the receiving interface. Going back to that example that I mentioned with 38 to 19, you'll choose the 19. If we can imagine the link being a 1 gig link, the outcome with a total would be 8 as opposed to 19, which is significantly lower, and the switch would prefer going over 2 hops as the opposed single link, which is 19. So let's get into the
Carlos here. This cost is very helpful in calculation because if let's say your backup, like you have your loop, but the loop is because you have a redundant backup link that is like 100 megs,
Mhm,
and all the others are a gig.
mhm.
So in STP calculation, it will be very simple for the STP calculation because it knows that that one like link is 100 megs. So I'm just gonna block that, and I'm gonna let the other gigs live. So just FYI,
Yeah,
that
it's
path
it
cost is very
definitely. Yeah, no, I think and that's great, right? That the switches are
yeah,
aware that the gig is significantly 10 times the speed
right.
uh, 100 meg link provides. So if we get into the root port selection logic, Mohammed, do you want to get us into that?
Yeah, so for the root port selection logic, you use the tiebreaker order. So you will look at the lowest path cost. So again, in this topology, it's the same topology from the earlier page.
Yeah.
You will look at the cost. So the cost from switch 0 to switch 1, which is the root bridge, is going to be 19. And then same for the switch 2 to switch 1, which is going to be 19. If we take the other way around from switch 0 to switch 1, if you go through switch 0 to switch 2 and then switch 1, that's going to be 38, and that's not lower than 19. So switch 0 will choose the link between the one that we have mentioned here, the destination port and root port. That link, and same for switch 2, it will use the bridge slash link, which is which has the cost 19. Next, it will use the lowest sender bridge ID, which is gonna be the upstream switch. Then you have the switch port priority, which you can set. Default is 128. And then you can also change the lowest switch port ID, which is gonna be the port number, is gonna also be in that tiebreaker process. But the main is always going to be, lowest path cost. You will go with that. Then you will go with the lowest bridge ID. Then you will go with the lowest port priority, which you can again change. The default is 128, and then the lowest port ID. And then again, the result is going to be one root port per non-root switch. So if you look at our topology, we have one root port per non-root switch. Yeah, that would be the selection logic.
Perfect. All right, so let's get into the topology changes and convergence issues. So when topology changes in spanning tree, the switch detects a change on a non-edge port. It'll send a TCM VPDU upstream, and then the root bridge sets the topology change flag in config VPDUs. So then the switch reduces MAC aging timer to forward delay, typically 15 seconds from default 300 seconds, flushing the MAC address faster. And the problems with legacy spanning tree are direct link failure, which takes 30 seconds to reconverge based on the timers that you mentioned earlier, and an indirect failure, which is 50 seconds while it goes through those 20 plus 15 plus 15 timers. And the impact of this is, 50 seconds is a lot of time to wait for a redundant link to be established. 50 seconds for big enterprises can mean thousands, if not hundreds of tens of thousands of dollars that are being lost. So this is why enterprises today move to that rapid spanning tree, which significantly lowers the convergence time. And also, there are other redundancy technologies that use once we get into link aggregation and so on, which we'll talk about in future videos. So with RSTP, Mohammed, can you give us what the key improvements are with this?
Yep. So Rapid Spanning Tree Protocol, or RSTP, is a much improved version of STP. Its main purpose is to be faster. And here in the key improvements, first of all, the standard for RSTP is 802.1W. So the converger process goes to about typically 2 to 6 seconds from 50 seconds, like we saw in traditional STP. And it can be much faster on the point-to-point links, like the links between switches. Simplified port states. So it has only 3 states where you have discarding, learning, and forwarding. The new port roles, you have an alternate, the backup to root, and a backup, which is a rare segment, same segment backup. The port types now you have is edge or port fast, which is immediate forwarding. It must pair with the BPU guard, which is another technology that can be used with RSTP. And then you have point-to-point, where you have full duplex links, and you use proposal/agreement handshakes. And then you have shared, which is half duplex, but it falls back to STP. The backward compatibility, it's compatible with legacy STP. As for protections, now you have BPDU guard, which shuts port fast port if BPDU is received. So BPDU essentially is there to protect the root bridge. You don't want your root bridge to be overtaken by another switch that joins the network and says, hey, now I am the new root bridge. Everybody just make me and update your topologies. You don't want that. So that's why you have your BPDU guard. You have your root guard, which root guard will stop the ROG root elections. Then you have your loop guard, which will prevent the unidirectional failures from breaking topology. And then you have UDLD, which is fiber unidirectional link detection. Carlos, if you have anything to add here.
No, other than, just take a look at that convergence time difference, right? Going from
Right.
50 seconds to 6 seconds. Um, as far as BPD, the protections, those are commands because in the end, that's what they are, and
Yeah.
directions that we give to the switches that are used in enterprises, very regularly. Where it's traditionally used is on the edge switches, right? So think of a
Yeah.
network, and there is a hierarchy. You have your access switches, which is the lowest level, where your endpoints, your consumers are going to connect. And you don't want you're not going to be checking your network jacks throughout the building every single time. So if somebody malicious and maybe not intentionally connects a switch because they got other devices that they would like to give network to, what that can do is we don't know what their spanning tree configuration does, and it becomes a ROG switch that can take down your network through, loops. What BPDU guard does is as soon as it detects a switch, because by nature switches will exchange BPDUs,
Right.
it'll error disable that switch port and stop the spanning tree process and just, completely saved your network from a terrible day.
Right.
But I'll get into the best practice and the summary of this video. What you're, some of the things that you want to check when architecting or deploying your network is make sure you manually configure your root and secondary spanning tree switches. Um, Ideally, in a collapse core network or a three-tier network, where your switch virtual interfaces that we've talked about, throughout other videos, that's where you want to configure the primary because that's where your layer three is going to get forward. That's where your layer two is going to get forward. You want to implement RPVST because it is significantly faster than traditional STP. You want to enable PortFast and BPDU guard on host ports or those consumer switch ports that I was talking about. What PortFast does is it'll skip that spanning tree process and go directly to forwarding. So that way, somebody connects a critical device to the network, you want it to immediately begin forwarding frames and immediately has network access rather than making somebody wait on the other end. Root guard on access to core uplinks. So we know that my root bridge will not be changing. Let's create a guard and a loop guard for globally for safety. So we'll use long path cost and high speed fabrics. Yep, we're not going to get into detail with that. And make sure you documentation, spanning tree topology and protections. Documentation is the most important thing when architecting a network. That there's no, I think every engineer in the world agrees with that. And make sure you test your failovers in a lab environment if you have the budget to do so, which most, you know, there's never budget for a lab environment. The key takeaways from this are that spanning tree prevents loops while keeping redundancy. The root bridge plus root design ports define the logical tree, and RSTP provides significantly faster failover than the traditional spanning tree. Guard features protect against mistakes and mispatches. Yes. So mistakes and mispatches means you introducing a new network device or new network switch to your network.
Right.
Right. So that pretty much concludes our slides. Mohammed, I don't know if you have anything to add. Thank you very much.
No, I think
Yes.
that's we've covered everything.
Yeah. And I think, when we're getting into all this theory and people just reading it and looking at diagrams, it is so hard to understand what is going on. So I would like to share, maybe we can do a live demo of how this process works.
Yeah.
I'm gonna switch over to a drawing here that I have live. Let me see once you can see it. Are you
Yeah,
able to see
sure.
that?
Hmm.
Does that look okay? Too small?
It looks okay. Yep.
Okay, great. So if I get into it and I pre-drew this prior to our call because I don't want, to make waste your time watching me draw switches and stuff. Um, what we have here is the three in traditional spanning tree. This applies to traditional spanning tree. Um, what we have here is the three type of ports that we can have. We can have a designated port, a root port, and a blocked port when we're talking about switches, right? So you'll notice here that this applies to VLAN 1 because all of my three switches have the default priority in them. So you'll see my priority. Let's go through the spanning tree root bridge election process, right? So the BPDU consists of what we know today, which is the VLAN ID, the MAC address, and the priority. Priority, they all look the same, right? So priority, that's a tie. We know that priority is a tie. Let's look
Mm-hmm.
at VLAN ID, and the priority consists of the VLAN ID. So we're talking about VLAN 1 and the MAC address. We know that a MAC address is a hexadecimal, um, contains hexadecimals. So here, for the sake of the example, we have 0, 0, 0, 0, 0, 0, 0, 0, and then 0, 0, 0. This is what differentiates 1, 2, 3. Okay, so we knew that switch 1 is going to be the root bridge. So let me go ahead and root bridge because it has the lowest MAC address. And the root bridge, the easiest one of these is that we know that every port that connects to a switch on a root bridge is going to be a designated port, right? So
Right.
we'll just go ahead and draw out our DPs here. So DP, DP, nice and easy. Oh, sorry, I should have probably made that black, huh? Because my
Oh, yeah,
will
because
be
of the
red.
coloring. Yeah.
Yep. So my DP is going to be here.
Mm-hmm.
DP is going to be here. Okay. Now let's look at the root ports, right? We know that the root port is going to be the port that forwards frames to the root bridge. So the ones that are directly connected. And as you'll notice here, everything is set at 100 Mbps, 100 Mbps. So
Yeah.
we know that there's a cost of 19,
Yeah.
19, and 19. What this means now, if I'm switch 2 and I need to get over to switch 1, which is my root bridge, this right here, if I go through here, and I go through here, this is a cost of 38. Well, I have a cost of 19 here on a direct link to switch 1. This will be my root port, right? Oh,
Yep.
I should probably make that blue. This will be my root port. So let me go over root port. The same thing, the same logic applies to switch 3. Switch 3, we have a direct connection to switch 1. Why would I take the 38 cost when I can just take a direct 19 cost? Let's go and label it a root port. Nice and easy. Now, where the fun begins is between switch 2 and switch 3. We need to understand which one is going to be the blocked port in this topology. And what's going to happen is the same thing, the same BPDUs are going to be leveraged to determine which port is the one that blocks and which port is going to be the one that is the designated port. Because the designated port is the path to the root bridge. It's not going to be a root port because it's not going to be forwarding anything. It's going to be the path in the event of a failure that takes you to the root bridge. Um, so in this case, again, same priority where things changes with the MAC address of the switches. So 0, 3 is higher than 0, 2. So what that means is 0, 2 is now going to be the root port, or sorry, the designated port. And 0, 3, because it has a lower, or sorry, higher MAC address, is going to be the blocked port. And that's what spinning tree is. It gets a lot more complex when you begin talking about six switches, right? But for the fundamental, this is how the spanning tree election process happens. Um, for the sake of another example, um, when we begin talking about different link speeds, I think we can do something like I'll draw it much simpler. So we'll have switch 1 and we'll have switch 2. Does that look like a 2? Yeah. Okay, cool.
Yeah.
Um, we'll do switch 3 here. Okay. And a link here. So let's assume this is 1 gig. Let's assume this is 100 Mbps. Let's assume this is 1 gig. And let's assume this is Mac 0, 0, 0, 0.
You can just say root
Oh,
bridge because it.
uh-oh. Okay, there we go. Yeah, so this is the root. Okay.
Yeah, we can just, yeah.
So this is root bridge. is the root bridge. Then this will be a DP. We know that this is going to be DP. We know that this
Right.
is going to be DP. So this is cost of 19, right? We know this is 19 cost. Oop, sorry. We know that this is cost of 19. We know that this is cost 4,
Yep.
and this is cost 4. So then that 1 gig port, let's see. Okay, so right here, I know that here I would have to transfer cost 4 plus 19. If I'm switch 2, I have to go from cost 4 plus cost 19 for a total of 23. When I have a direct connection to my root bridge on a cost 4, this will become a root port, right?
Right.
Then if I am switch 3 and I have a direct path to switch 1 on a 100 Mbps link, which is a cost of 19, here, if I transverse through an extra hop, which is switch 2, my total cost is 8. So what will end up happening is that because this cost is significantly lower than the 100 Mbps link that I have a direct connection to, I will actually become the root port. And
Right.
I will become a designated port, right? Because switch 2 became a path to get
Yeah.
to the root bridge of switch 1. So because it became a path, this will become a blocked port. And you see how this is still a DP, this is a B, and this is now a DP, this is an RP, and this is a DP. So that's how different link speeds can influence the spanning tree process and how the 1 gig or extra hops may end up being the best path depending on slower link speeds. And that pretty much concludes my drawing process. I apologize for the several drawings on the second one. Um, did you want to add anything, Mohammed, or do you want to get into the lab portion of the video?
Let me see. No, it looks pretty good. I think we cover everything, the basics.
Yeah, it's the basics, and this is such a
Yeah,
3 4 hour long topic
right. It's a
on
very
spanning tree in
complicated topic.
general. I don't want to get into what our STP is, and we end up being here for 4 hours.
Right. I
So what I'll do is I'll stop sharing and get into the lab portion of the video. It is going to be very simple. Just kind of do the different show commands that we can leverage when talking about spanning tree. Let me go ahead and pull that up. Okay. Let me know when you can see that. Are you able to see that okay?
can see that.
Okay, great. So what we have here is I have 2 labs. Okay. The lab objective for lab 1 is to understand basic spanning tree selection process. Um, Basically, just to see which switch becomes the root bridge. As you'll notice, we don't have that triangle diagram, so there won't be any blocked ports or any, well, there will be designated port, but there will be no blocked ports. So what we'll do is, let me go ahead and pull up the terminal, which I should already have open. Right, so switch 2 and switch 3. Okay, so if I enable all of these, okay, if I do show VLAN brief, you'll see that the only active VLAN is the default. I have not configured anything. And the same applies for switch 1, switch 2, switch 3. So if I just do the show spanning tree VLAN 1 command, what does it do? Well, so what it outputs is here we have what does spanning tree look like for VLAN 1? The root ID is 32769. This is the MAC address. And look at this right here. This bridge is the root. Then it goes on to talk about the timers. and the bridge ID, which is myself, in this case for switch 1, this switch is the root. So switch 2, switch 3 will forward their frames to switch 1. So if we go look at what this command shows in switch 2, show spanning tree, VLAN1, look at that. We know that the other switch has switch 1 has a MAC address of 9A00. So it goes to the root ID. Yep, so my root is switch 1, and this is who I am. I am 9B00. And look at this. We know that we're leveraging gig 00, so that becomes an RP, a root port. And
Right.
this is, look, all my ports are DPs.
Mm-hmm.
This is an RP, right? And if I do the same command here, show spanning tree, VLAN1, the same applies. My root is 9A00. These are the timers. And my port being leveraged is gig 01. My cost is 8. What does that mean? I have to traverse two 1 gig links to go across to my root bridge. So my 4 plus 4 that we spoke about earlier is 8. And if we were to add a 10 gig link, you know, two 10 gig links do this, we would prefer that 2 over 2 and so on. But as you'll see here from this command, we have an RP, and all of our ports for now are DPs because they will all take us to that path, right? To that root bridge.
Right.
So that is very easy lav. If we were to go on to create VLAN 10, VLAN 20, VLAN 30, and we defined we just left the standard priorities, the same outcome would happen. So best practice would be to go onto the switch and say config T, spanning tree VLAN 1, priority. We can do 0, which is, basically do not, this will be the root. It is the same
Yeah.
as saying anything lower priority. Ideally, you want to
Right.
do 0, or you can just do root. So I want this to become the primary root bridge. So if we issue that and we do that show spanning tree command again, show spanning tree, VLAN1, you'll see that now the priority has changed because it noticed that the other switches have that 32769. It'll just lower it by 2 times 4096. So the same will apply. Ideally, you want to set the priority to 0, and it'll be much. You basically close any attack vectors from somebody adding a new switch with a lower priority.
Right.
Right. So that's the selection process. Let's get into actually looking at the other port states. And if I go to my switch 4, my switch 5, and my switch 6, I'll close these out. Let's take a look at switch 4. So switch 4, in this case, now that we've added that extra link, which would create a loop and a network with no spanning tree being leveraged, we would do show spanning tree, VLAN1. Oh, okay. So in this case, I am not the root. So switch 4 is not the root, and we see that, well, we found the blocked port. I wanted to leave it for last, but I wasn't sure which one. But you'll see here that the priority is 32769, priority 32769. So the root bridge has the same priority, but you'll notice that it has a lower MAC address. Let's take a look at that. The address, the root ID, the root bridge has a 505 as opposed to a 50D. So 505 is lower than 50D,
Right.
and that's how that root bridge got elected, which we'll find which one it is. As far as let's look at our interfaces, you'll see that gig 00 in which is this link here, 206, is being blocked right now. So gig 01 is my RP. Okay, so this
Mm.
link here is my RP. That gig 01. So I'm going to make a wild assumption here that switch 5 is going to be my root bridge.
I
If I
think
go
I
to
agree
switch
on that.
5, let's see. If I go to switch 5, I do show spanning tree, VLAN 1. Look, let's see, root ID
Yeah,
505. Yes, this bridge is the root. Yep, because you'll see that the root ID, this bridge is the root, because the root ID is 32769, the priority, and the MAC address is 505, which is the lowest amongst the three. And you'll see here that Ethernet 1 and 2, or gig 01 and gig 02, in this case are DPs. They're DPs. And we know that all the ports will be DPs because I am the root.
right.
Um, so that's if I go to switch Euro 6, I'm gonna take, let's I'll kind of give 5 seconds for somebody to pause this and try to guess what the switch port rules are gonna be. Um, and we know that Ethernet 2, or in this case, gig 02 for switch 6, is going to be a root port because it's going to be the link that takes you to the root bridge of switch 5. And we know that Ethernet 0 in the topology, or gig 00, is actually going to be a designated port because
Right.
the other side is blocking, and that is the path that as soon as that becomes active, will take you to the root bridge. So if we go to switch 6, and we do show spanning tree, VLAN 1. Okay, exactly. So here we have the root port, which is gig 02. That takes us to switch 5. That is the path to our root port. And we know that Ethernet 0, or gig 00, is a DP because when that port becomes um, unblocked, if there's a link failure, then this will be forwarding to the root bridge.
Yep.
So I think it would be great that we simulate a link failure and how that creates redundancy across links. So what I'm gonna go ahead and do is kill this link here, Ethernet 011 or gig 01 on the two switchboards, and we'll see here, gig 01. Okay. All right. So now that we've killed this link, and spanning tree is going to be a 50-second timer. But what spanning tree has done now for us is we were able to create a redundant path. And in the real world, a mouse could have chewed my cable, and now I have to transverse um, this path now, going through switch 6 to get to my root bridge. So let's check now what switch 4 is in. Look at that. So line protocol change stayed down. So we're getting some logs now that that link went down. Now, in theory, gig 00 should now become a root port because it will begin forwarding frames to the root bridge through that path. So if I do come down here, show spanning tree VLAN 1, look, gig 00, what was previously a blocked port, is now an RP port because it's forwarding frames to the root bridge. So nothing should have changed in switch 6 because it was always a DP. We know that. Switch 6, nothing's changed because it was always the best. It won the election process between switch 4 and switch 6. So that's how we simulate a network failure and how spanning tree can be served for redundancy. Obviously, the same logic applies with RSTP, which is what enterprises are doing today. It's just a bit of configuration quirks, which hopefully we can go into one day, or you'll see as you continue your education trying to get your CCNA. But thank you, Mohammed, very much for putting this together for us. Is there anything that you would like to add to this?
Um, let's see. No, looks good.
No. Okay. Well, thank you everybody for watching this, and thank you.